Hi, and welcome to the 8th video in our series of presentations about using Rhapsody for systems and software development. My name is Jeff Cohen, and I'm with 321 Gang. In this penultimate video in the series, we're going to talk about modeling behavior. As I said, this is the 8th video in our series. As always, the videos stand on their own, so if you haven't seen the others, you don't have to go back right away to go see them all. But you may want to go back at some point and watch the others. Behavior. Okay, so what are we talking about? So behavior, along with structure and interactions, define a block. Really, it defines the system. Structure defines the pieces. Interactions define the communication. Behavior defines what the block does when it receives the interaction. So in other words, you get a message, what do you do now? What do you do with it? Now, in a previous video, we talked a lot about activity diagrams and actions. So if you want to see more about that, go back to that video. Flowcharts are another way to show behavior, but again, most people are very familiar with the basic concepts of flowcharts. They're really good for showing an operation in certain cases. So we're going to concentrate today on state charts. State chart is very simple behavior. It's aperiodic. That means it waits for something to happen, something to occur. When that thing occurs, when that message is received, it's very well defined. It only makes the transitions on those defined transitions, and it only goes from one known state to another known state. So the transitions occur on these event lines. And these are the states. We also have a default transition, but that just shows you where you're going to start out, and that's pretty obvious. So let's talk about this just a little bit more. Very simply, we're going to start out in the up state. We're going to receive an event of a press, and when we receive the event of the press, we go into the down state. We stay in the down state until we receive a release. There's another reason why state charts are so powerful. One of them is that you're going into software with a design pattern. That means it's something that's very well understood, very well known, very repeatable. If you ask your software folk, have they ever made a mistake with a state variable, forgetting to clear it, or not properly initializing something, all of them that are being honest will admit, yeah, I've screwed that up once or twice. But by using the pattern, you've already proved it, and you know that it's going to work. This is just like for the mechanical guys, that book of mechanisms, that 4-volume set of mechanisms that a bunch of us have sitting gathering dust that show how to build things, and we're always going to do it the same way. That's what the design pattern is all about. And that's what makes a state chart a very safe and good way of implementing things. Let's get to more detail. So the behavior of a state chart is very simple. I'm going to start down in this blue box. I'm going to start in the up state. That causes me to transition. I'm starting the up state. The only way that I'm going to transition is if I get this EV press. If I get an EV release, I just stay in the up state. I get an EV press and I go into the down state. As soon as I go in, I start a timer for this timeout. If the timeout occurs, I take this action of reset and I go back into the down state. I stay in that down state. Why? Because I haven't gotten the release to go back to the up state. It's really all it is. In SysML, we define 4 types of events: a timeout event, a signal event, a call event, and a change event. A timeout event just comes from a timer. It happens when a time is reached or when a relative amount of time has elapsed. In our previous example, our timeout was right here. So in 2 seconds, this is in milliseconds, we'll transition out of the down state, perform our reset, and then transition into the down state. A signal event is one of the more common ones. It's when something of interest happens, and it's generally performed asynchronously. That means that it's being performed at the callee's context, the context of the state chart. It's not happening at the caller's context. That would be a call event. We'll get to those in a minute. So the event is received, and it gets handled at the appropriate amount of time. In our previous example, EV push and EV release are both examples of signal events. Now, within IBM Rhapsody, the synchronous signal, or the asynchronous signal, is an event. These are built into the Rhapsody framework. For the software guys, this is part of that design pattern, and queuing it up is not something that they have to build each time for themselves. It's something that comes as part of that framework, and it can be built into your application with no additional license requirements or anything like that. That's something that's free for you to use to be able to build your systems. On the system side, you use the same event to perform the transition, and you can also use it to validate your system and to see that the model is correct. It's doing what you want it to do with model execution and visually confirmation. So the sister of the signal event is the call event. This is an operation that happens in the caller's context. It's something that you want to happen right away when called. So, for example, if you were building a time-related system that had to use a Tuscan transform, that time is very important. You wouldn't want to use another event. You'd want this to happen at the caller's context. In Rhapsody, in that same framework I was talking about a moment ago, these are referred to as triggered operations. Finally, there's a change event. This is an event that happens when something is being monitored and it changes. Generally, I use these in state. So I'm in, for example, the down state, and I may look for something to change. Not a switch going from pushed to released or something like that. Use the change events sparingly, because they can get you into trouble. They don't use all of the same design pattern that we have with the rest of the state chart, and it can cause you trouble. On this slide and the next couple, we're going to talk about some things that we have to watch out for, some minor danger points. The first one is the order of operations, the way computations are performed. Actions can be performed on entry, on exit, on transition, within the state, or on a timeout. But the order that they're performed is very important. On a transition, they're always performed, check the guard, that's going to say whether or not you take that transition, then perform the action on exit, perform the action on the transition, then the action on entry. Let's add a little mess to that. If I've got nested states, which we'll talk about in the next couple of pages, those order of action on exit start from the outside or from the inside out, and on entry go from the outside in. Always important to do that. Now I mentioned a guard just a second ago. A guard must evaluate to a Boolean value, and that Boolean determines whether or not you're going to take the transition. What's important here, though, is that guard is always executing. If you change a value while you're calculating that guard, it's changed, even if you don't take the transition. You can check within Rhapsody if you're in a state. For example, if you have a more complex transition, and again, I'll show you a couple of these later, you can check to see what state something else is in using that is-in macro. And that can be used in a guard. As a matter of fact, it frequently is. But again, remember the order of operation. It's always guard, actions on exit, actions on transition, action on entry. Here we have a little more complex state chart where we do have some embedded states or nested states. And in Rhapsody, you can pull up the features window, and that's where you would put your actions on entry and actions on exit. You can also, by hitting the little icon here in the corner, show the actions when that would be occurring. Generally, I don't like to use those. I find that they clutter up the diagram, and unless you've got a lot of room, I find it more confusing. And I've got the icon in the corner there to tell me go ahead and open it up and take a look at it. So as long as we're talking about nested states, let's talk about nested states. The key of a nested state is that when I'm in pressed, for example, I'm in both pressed and down. But it's still exactly one known state to the system. I'm in the pressed and down state. When I make the transitions, I can show the transition either coming in to a state and then going into a default, or I can show it like this, going directly into a state. There are times when you want to show this going directly into a state, and that's when you have a condition where you have one specific state where you want to go into. But in this case, they're basically the same. So I ask you, are these two the same? Would I have the same behavior? I'll give you a second. Now, let's take a look at what you have here going from the up state to the down and pressed state. So first we're going to perform the guard. Well, there's no guard here. So I'm going to go from actions on exit of up. There's no action on transition. So I'll perform the actions on entry to down and the actions on entry to pressed. How about over here? Well, again, I perform the guard. There's no guard. I perform action on exit of up. I perform the action on the transition to press. Again, there is none. And I perform the actions on entry to the down state and to the pressed state. So these two are actually functionally the same. If you've got Rhapsody, you can go and prove it. Put a little printout statement in there and run it and see what happens. There are times when we're going to transition out of a state, but we actually don't want to truly leave. We want to have, for example, always go back into the same state. In this state chart fragment, what you've got is a transition going from the off state to the on state. When we go into the on state, we're going into the on and monitoring state. If we were already filtering, we want to go back into the filtering state. If we were in an alert, well, we want to stay in that alert state so that we don't send out multiple alerts. That's why we have the history. You have to make sure that you initialize a history connector before you use it. If you don't, it's not going to work the way you think it will. And it may send you off to not some unknown place. It'll send you to the default, but not necessarily to the history. So that's why I show it like this, from the default transition into the history connector and then into the state. A little more on the history connectors. Their purpose is to return you to the state you were just in. But what if there's substates below the state that you're in? Well, we have a deep history connector that's going to take you to all of those substates. The shallow one is just going to put you at this state chart, or this state's level. So in this case, if there were states below :on, and you returned in the history connector, we would, using a shallow connector, just go into :on. If we use a deep connector, the way it's shown here, we would go all the way down to anything that's below the : state. Important to note, you can only have one history connector per state, which makes sense because you're either going to go all the way down into the deep state, or you're going to stay at that shallow connector, which is going to put you in the default state. One of the more complex state chart is to have parallel regions in a state chart. In this case, we're in the on state, but we're in both this top part and this bottom part at the same time. A transition out takes you out of both at the same time because you're transitioning out of the on state. A transition in will take you into the on state, and it will take you to where you would be each of these as though they were independent states. Now, what's cool about this is they can be aware of each other, or they are aware of each other. So we can test using that is-in macro that I talked about before to know whether or not we're in the state. So what's going on here? Why does this make sense? Well, we have two states. We're either monitoring, or not either. We're monitoring, and we know whether we're filtering or whether we're in the alerting state, and we know whether or not we're performing maintenance. So we could be normal and filtering, or performing maintenance and filtering. And these are happening at the same time. When we turn the pump off through a stop, we stop the pump no matter which one we're in. Same thing when we have a fail. We indicate that fault. I know that these are far more complex than most folks are going to use on a regular basis, but they are pretty valuable, especially in the systems engineering world, to build up different functionality of a system. You can have one block that defines the states and modes, and that parent block will allow each of the use cases that you're building out to have the states in parallel here for the different things that they're trying to do, completely unrelated. As I said, in this case, we're up here monitoring the back pressure of a pump. In this lower region, we're performing maintenance. We're either on or in normal mode or we're performing maintenance. These things are completely independent of each other. They just happen to be happening at the same time. And therefore, we can use the parallel states. I know that was just a really quick overview, but it hopefully will get you going. In the next video, I'm going to give some best practices for modeling within Rhapsody and some good things that you can do with that. Hope you'll join me for that one too. And of course, as always, if you need any consulting or training or mentoring or products for systems engineering, please reach out to 321 Gang. You can contact us at our website, www.321gang.com. You can also take a look there for a lot of good technical information. There's articles, other videos, white papers, a couple of ebooks, and things like that. Thanks a lot.